All right. Hello, everyone. Thank you for joining. My name is Renee Soto, and I'm a sales engineer here at Platform9. Today, I am looking forward to talking to you all about elastic machine pools. So elastic machine pools, by definition, it's not an autoscaler, nor is it considered a FinOps tool, but rather we consider elastic machine pools to be a highly efficient compute engine for public clouds. So at a high level, what it does is it creates like an alternative hypervisor virtualization layer on AWS bare metal, and then it leverages a virtual machine over provisioning, along with live migration to improve resource utilization beyond what's currently possible with other solutions. So before we jump into the demo, let's review some key concepts to help set the stage. So this graphic here, this represents a standard EKS cluster. This EKS cluster has 9 worker nodes, each of which are running on the M5 4x large instance type. So it's fairly straightforward. Now, let's keep that EKS cluster configuration from the previous slide in mind. So what EMP does is it would provision a bare metal server from EC2. And with our software, it deploys elastic virtual machines, or also referred to as EVMs, that will run as Kubernetes worker nodes that are part of your EKS cluster. So EVMs are virtualized instances running on bare metal servers, and an EVM looks and feels exactly like a regular EC2 instance. So with this model, the EKS cluster can run the same workloads, and it'll have the same resources as the EKS cluster I showed you in the previous slide. But now, in this specific example, instead of paying for 9 EC2 instances with EMP, you're now only paying for the M5 metal instance, which results in significant cost savings. And this is just the beginning of what EMP has to offer. So let's go ahead and move on. So now I'll show you how you can easily revolutionize your EKS clusters by walking you through the EMP creation process. And then once we have that down, we'll move on to auto scaling, and we'll review our cost savings in the EMP dashboard. Okay, so what we're looking at here is the user interface for EMP, and I'll show you around some more in a bit, but I'll start off by showing you how easy it is to configure EMP so you can ultimately unleash some significant savings. So let's go through the wizard. So the first step is where we'll specify the name of the EMP we want to create and select some options related to the EKS cluster that we want to utilize. So let me give this a name really quick. And now we'll select the cloud provider. So prior to this, I used the user interface to securely authenticate with my AWS account. So I'll select that account here along with the region where my cluster is deployed. And here I'll select the cluster that I want to associate with EMP. You'll notice that one of the clusters is grayed out. This is because this cluster is already part of an existing EMP instance. So I'm going to go ahead and select the available cluster I have in this region. And for the next step, we'll need to ensure that we have security group rules in order to enable communication between the EKS control plane and the elastic virtual machines that will be deployed. So here I'm gonna leave the default option so that way the rules are updated automatically. So that's pretty nice. And again, this is just one of the ways that we leverage automation to simplify the installation process and make it as easy as possible for you. Now, the last part in this section, we'll need to enable communication between the EVM nodes and the workloads that are currently running on the existing non-EVM nodes that are part of the cluster. So here I'll select the security group here, and then we can move on to the next section. So in this section, here we'll configure the bare metal pool. So here we'll specify the AWS bare metal instance type that will be used for the bare metal pool. I'm going to go ahead and select M5, the M5 metal instance type. And then we'll provide the availability zones where the bare metal pool, where the bare metal servers should be created across. So EMP will deploy at least one bare metal instance in each availability zone. So if I have one bare metal server, let's say, for example, it'll be deployed in US West 2A. And then as another bare metal server gets deployed, whether it's based on my full configuration or auto scaling event, it'll be deployed in another availability zone. Now we just select the SSH key that I will use to access the bare metal instances. This drop down here is populated from AWS. And then one of the last things we need to update here, we'll need to we need to select the public and private subnets that are part of my VPC. And then lastly, we'll set the minimum and maximum number of bare metal servers that will be deployed in this bare metal pool. So we'll set the minimum number to 1, and we'll set the maximum to 3. So with this configuration, it will deploy a single bare metal bare metal server, and it'll create additional ones as needed. And I'll get into all those details shortly. So the third section as part of the wizard, here we will set the configuration for the elastic virtual machines that will be deployed on top of these bare metal or inside of these bare metal instances. So I'm going to go ahead and select M5 4x large, as well as the public SSH key. And then here we can set some overcommitment ratios. So with the default overcommit ratio of 1.5 and the instance types that I selected at the EVM pool and the bare metal pool levels, this should allow me to have approximately 9 elastic virtual machines on this single bare metal instance. And lastly, I can specify the minimum number of elastic virtual machines that'll be created, and yes, Madhur.
Chime in here. The overcommitment ratios, I think that is one of the very important aspects of EMP, because that really determines the amount of over provisioning that we would be doing. So essentially, the ratio here decides how many virtual machines we should put on a single bare metal server, and what ratio of the bare metal server's actual physical capacity should we over provision to. So as really 1:1.5 for memory for over provisioning. This would mean if a physical server has 10 GB memory in a simple case, then we would provision VMs where the sum total of the VM's memory could add up to about 15 GB. And the same thing for CPU. And you can see that in the default settings, we set CPU over provisioning to be very high. And this is because in most workloads, in most environments that we see, memory is the most constrained resource versus CPU tends to be more highly available. But if in your environment CPU is the more constrained resource, then you would change the CPU overcommitment config and set it to a different value.
Very good point, Madura. Thank you for highlighting that. Yeah, it's very important to cover that. So thank you. So as far as the wizard goes, those are the only details that I need to provide. So if I click next, I'll see a summary of all of the options I had selected throughout the wizard. And then as soon as I click create, the installation process will kick off. So to spare some time, I already provisioned EMP on one of my clusters, and I'll come back to this in just a bit. So now that we've created an EMP with our EKS cluster, EMP is continuously monitoring the resource utilization. So that way it can dynamically scale resources based on demand. And there's a few different ways that we handle that, which I'll get into shortly. But first, let me kick off this chaos experiment that I have. And what it's going to do is it's going to generate load on my EKS cluster that I just created with similar settings. So, and this process will take a few minutes for it to actually generate load on the cluster. So in the meantime, let's go over a few more concepts. So like I mentioned earlier, EMP is continuously monitoring and evaluating the current workloads and the resource utilization. So in order to ensure that the maximum infrastructure utilization is achieved, but while also ensuring the uptime and performance of your workloads, we have the concepts of bare metal auto-scaling, EVM rebalancing, and EVM auto-scaling. So we'll start with the EMP metal auto-scaling. So earlier, you saw how we had EVMs running on a single bare metal server. But whenever our tooling detects that the underlying bare metal server reaches 80% of either CPU or memory utilization for a certain period of time, EMP will automatically deploy an additional bare metal instance to provide that additional capacity for these elastic virtual machines. And it's important to note that EMP was designed with cost savings and effective resource utilization without sacrificing performance as some of the most important objectives. So I just covered the case where workload demand increases, but whenever the workload demand decreases, we'll also safely scale down the bare metal footprint without any impact to your applications, and that'll ultimately spare you the cost of these metal EC2 instances whenever they're not necessary. So you may be wondering how we effectively ensure the uptime and performance of your workloads. So remember, each of these EVMs here, they represent a node in Kubernetes that is attached to your EKS cluster. And we have a component called the rebalancer, which plays a critical role in allowing us to ensure the uptime and performance of your workloads as the bare metal scales up and down, right? So one area where it comes into play is whenever there is a bare metal scaling event. So in this scenario, whenever a new bare metal server is deployed to the pool, the EVMs will be evenly distributed across the underlying infrastructure. And we do this by leveraging unique live migration techniques to effectively migrate the workloads from one bare metal server to another while ensuring zero downtime to your workloads and ultimately ensuring that your applications SLA is always met.
And Renee, just chiming in here because this is a really important aspect of EMP, because many times we get asked, well, as you move these EVMs across bare metal nodes, I'm sure there's going to be a part disruption, a part downtime, and how do you handle it? Do you make sure that the parts get restarted on the other nodes? Do you make sure to not do this for deployments that have single replica? And so that's why it's very important to call out what Renee just said. This technology results in absolutely zero part disruption, because what we're doing behind the scenes is actually very cool. We live migrate these virtual machines from one bare metal node to the other, right? And so what the live migration entails is we would be behind the scenes copying all the context of the virtual machine, all of the memory, all of the storage state, networking state, etc. And at some point, we have to do a switch where the source virtual machine is frozen for maybe a millisecond, a few milliseconds to a second, and it's resumed on the target metal server. And any application running inside that virtual machine would not know that the VM has paused or moved or anything has changed. So this completely retains your application SLA 100%.
Great, thank you, Madhura. So yeah, so in addition to the rebalancing, another critical component of EMP is the EVM cluster auto-scaling, right? So let's take an example. Let's say that there's a period where Kubernetes resources are continuously getting deployed onto the cluster, and with that, you perhaps start seeing some new pods in a pending status because they're unschedulable, perhaps because all the the nodes are fully utilized. So if unschedulable pods are detected at any point, our EVM autoscaler will immediately kick in and create new EVMs to serve those Kubernetes workloads.
Yeah, and just to chime in here, it's what we use is a standard AWS cluster autoscaler, and EMP just taps into it by having an EMP EVM provider there and an admission controller. So essentially, EVM autoscaling works exactly the way it would work for you today for your EC2 nodes if you're using AWS autoscaler. If you are using tools like Carpenter, we're compatible with them too. We can also work with a Carpenter autoscaler because EMP is a technology that works completely behind the scenes.
Good stuff. So now that we have those concepts laid out, let's go ahead and head back to the EMP user interface. And let me go ahead and refresh it. So I'm going to go ahead and click on the EMP that I have created. And remember earlier, I kicked off the experiment that generated load on the cluster. And with that, we're able to visualize easily visualize the amount of memory utilization, right? So here we could see that this is at 99% utilization at the moment. And we can see more details as well by clicking on the EVM pool, and for each node or EVM listed here, we'll be able to see, or we'll be able to visualize the current resource utilization of each EVM at a quick glance. So as this so soon I'll show you how else EMP responds to this increased resource utilization. So I'll come back to this UI shortly, but in the meantime, let's go ahead and jump over to the next section. So in our user interface, we have a cost saving dashboard that will help you view your realized savings with EMP, along with some annual savings projections. But we'll take a step back really quick, so I can set some context and give you a cost savings example. So in this example, we have a standard EKS cluster, and to clarify, by standard I mean just an EKS cluster without EMP. So this particular EKS cluster, it has 15 worker nodes deployed as M5 4x large instances, deployed in EC2. And the on-demand price for each instance is 77 cents per hour. So when you take 15 instances at 77 cents per hour, you're looking at an annual cost of about $101,000. And so whenever you take this entire environment and you put it on a single M5 metal, for example, the cluster size is the same, the amount of compute you get is the exact same, but now the cost after EMP is it comes out to about $41,000 annually, and that's because the single bare metal instance runs at $4.77 per hour, and you're no longer having to pay for each individual instance that is part of your cluster. So you're only paying for the M5 metal instance. So that's what the difference is here. Is there anything you want to add to this?
No, I think you covered it well.
All right, thanks. All right, so let's hop over back to the dashboard, and we could see some of the realized savings. So the cluster configuration that I currently have is a little bit different than the one I had have in the presentation. However, there are a couple of things that I do want to highlight. The first one being is the projected annual savings. This is based on what how my cluster was deployed whenever I initially configured EMP, and now with the new and with the bare metal footprint. So it's highlighting here that my annual spend prior to EMP for this one cluster was running at approximately $70,000 annually. And now with EMP and running this on the bare metal servers, now the annual spend is down to $43,000 about $43,000 annually. So we're looking at about a 39% savings in this one particular example. And the year-to-date savings, the reason why it's that value is because I had just created this cluster very, very recently. So this is, literally the year-to-date savings from the time where I started using EMP. Oh, it looks like we have a question. Madhura, would you like to take that one?
Yeah, so there's a question here that says, if I add Carpenter, would I get another 10% on top of EMP? And the answer is no, simply because EMP already does the same savings. EMP covers for the savings that Carpenter provides to you today. So let me explain this. What Carpenter does is it right sizes your pods. It'll essentially create an VM, an EC2 instance per par, or it'll make sure that it's spinning up the right sized EC2 instances so that there is no wastage, after you place pods on that EC2 instance. But the way EMP works, because EMP is completely utilization aware, and because it does over provisioning, it already covers that bucket of wastage, which Carpenter tries to address, and it does more. So EMP addresses what we call the unallocated capacity. That's the pie chart that's showing it here, but it's not fully populated because we haven't had this EMP instance running for a long period of time. But that's something we focus here in the EMP UI, which is the unallocated capacity and allocated but unused. So unallocated capacity is stuff that would go waste because of bin packing wastage, which was Carpenter does. EMP also addresses that, but EMP goes one step further, and it optimizes the allocated but unused capacity, which is where your requests and limits are high, but they're not actually getting used. So you won't get 10% on top, but you would get more savings, a lot more savings than you would with Carpenter.
Thanks, Greg, for that question. I've been kind of monitoring the environment in the background as I've been running this this experiment that's generating the load. And since that load was generated, I can now see that there are now a total of 2 bare metal machines in this as part of this EMP. And so whenever this new bare metal machine is added to the environment, if I go to the EVM pools, soon I'll start to see some of these EVMs going into a migrating status as our rebalancer process kicks in and redistributes the workloads more evenly across the bare metal infrastructure. And again, this is all
so this is really where sorry, Renee, I was just chiming in to say this is really where the magic of EMP starts to happen, where you will see in a bit, like Renee was explaining, some of these VMs transitioning to migrating state. And if you were to SSH into one of these VMs and run something like ping or so, you would actually see that command running even while the VM is migrating. So there isn't any change to the VM. The app keeps running just as expected, even while behind the scene the migration happens, and hopefully we'll see that. So really great stuff. There's a question here, Renee. Can we take it now, or is there something you want to cover first?
Sure, we can go ahead and take it now. Let's see here. I haven't worked with metals before. Is it only the M5 metal supported or other metal family as well? So I'll start with that. We do support other bare metal instance types beyond the M5 metal. So I was just kind of using that one as an example. However, if I were to go through this process really quick, I could show you the list of available instance types for bare metal. So here on this section, there are 12 available metal instance types to choose from. So,
and if I may chime in, Renee, while you're showing that.
absolutely.
Yeah, so essentially what AWS does, it makes a metal instance available for every single family of instances that it provides today. So for C5n.x instances, there is a C5n.metal. If you're using M6i.x instances, then there is an M6i.metal instance available. So essentially there's a metal instance for almost every family of or category of instances AWS provides. And so that's really the benefit. So we're able to, depending on what instance types you use today for EKS clusters, and it may be because you're using compute optimized instances or memory optimized or network, there will be a metal instance corresponding to that we can use. And then there's a second question as well. What is that C5n.4x large showing? So that one, Renee, if you could go to the EVM pool real quick, that's where we're showing that. Basically, what we've done is these EVMs are virtual machines that we're deploying, right? And so we allow you to specify what size of these virtual machines you want to deploy. So if you go click in that EVM pool for a second, Renee, and that's where, so here at the top, yes, the VM is migrating. But if you scroll up for a second, Renee, here in that overview, we show C5n.4x large as instance type over here. I think that's the one you're referring to. And what we're saying here is all of these EVMs in this EVM pool, they're created using the same instance size. And that's the C5n.4x large, because that's the size that Renee chose. Because in this example, his workloads on EC2 were running on that instance size. So he chose the same instance type with EMP. Now, behind the scenes, Renee, I think you also chose C5n.metal, right?
Yes.
For our metal instance. So that goes back to what we're saying. Exactly. Yes. So we mimic the EC2 instance types just to also make it easy for you to relate to what you're running before versus what we're running after. Although we don't technically have to, we could provide instance types that fit more to your use case, because we don't have the same restriction as AWS in terms of what instance types we have to support. Great. Renee, over to you.
All right, no, thanks. So yeah, so the other thing I was just going to briefly show, which we kind of already highlighted, is now that second bare metal server is up and running, we'll see this instance going into a migrating state. Shortly, it'll go back into a running state, and then we'll ultimately, be able to see the workloads more distributed across the bare metal infrastructure. So beyond that, yeah, so I mean, that's just, one of the many ways that Platform9 can help provide your organization with significant cost savings and, more effective resource utilization. And, personally, one of the things I like about it the most is just how simple it is to implement, to add to your existing EKS cluster, and some of the flexibility that we provide. So yeah, that covers the cases that I had as far as the demonstration goes. Madera, was there anything else?
Yeah, I was wondering if you have a session going SSH into this EVM, and no worries if you don't, but if you have, we could run something like ping and show users how the instance keeps running while behind the scenes it is migrating. And while doing that, there is one more question. Can I run a mix of default EC2s and EMPs? And yes, the answer is yes. So in a cluster, you could have some EC2 VMs and some EMP EVMs. And then what you would do is you just taint your workload to determine which workloads should run on EMP EVM nodes. In fact, that's the only way we determine which workloads should run on EVMs. And so you could taint all of your workloads. And so everything in a cluster runs on EMP EVMs, or you could run in a mixed mode, like you're saying.
And yes, and Madura, so I'm currently, I have a SSH session on this particular EVM that is currently in a migrating state. Just doing a general ping, and everything is looking good so far.
Fantastic. And this is another question we typically get from users. We have critical workloads that they can't experience downtime. We have Java workloads that require a very slow start and a lot of state, and so they can't even get disrupted, and therefore we can't use tools like Carpenter because we can't handle the part disruption. And EMP is a great fit for a lot of these Java applications. In fact, with Java, there's another thing that happens, which is that the JVM touches a lot of memory and doesn't always do a good job at freeing it. But EMP is actually able to detect that behind the scenes as well and look at active memory set for Java and do interesting things. And so that's kind of the beauty of EMP. And then the other aspect we get asked is, well, will the live migration impact my VM's performance? If it takes many minutes, will my application be paused during that time? And the answer, as we're showing here, is no. Because the VM will continue to run exactly the way it is, no resource starvation while it's being migrated, and there'll be only a very short, like a few milliseconds, maybe a second of what we call blackout period. And during that blackout period, the VM just momentarily freezes, but nothing on the VM gets impacted. And we might actually see it here. While that's happening, we'll take the next question. Regarding cost savings, apparently metals have a higher minimal cost as it comes with big resources. Would it still make sense to use EMP for small workloads on EKS? For example, parts running on a couple of C5.large, is there a minimum setup for EKS that would make sense considering moving to EMP? So yes, absolutely. There is a minimum setup because you're right, metals are, large capacity. And so the requirement is that for your EKS cluster, for whatever portion of workloads you would want to put on EMP, the sum total of the VMs, you can take either CPU or memory depending on what is your constrained resource today. The sum total needs to be at least 1.5x to 2x one bare metal node, right? For us to be able to give you savings. So for example, let's take a simple case. Let's say the smallest metal size on AWS has, actually, I think C5N is the smallest metal size, I think, Renee, right? And it has about 192 GB memory. I think for ARM instances, there may be a smaller metal type, but we don't support ARM yet. We're going to add support for it. So the C5N, if I'm correct, it's about 192 GB memory. Let's say that is the smallest instance on AWS. Then the sum total of all of your EC2 VMs today for at least one EKS cluster will have to add to that much, and ideally more, right? 1.5x to 2x more, so that EMP can still give you those savings. And so for really small workloads, really small EKS clusters, it doesn't make sense. Now, one thing I do want to call out is we have the technology to put multiple EKS clusters on the same underlying metal box. Okay, so you're not necessarily constrained by a single EKS cluster boundary. You could put multiple of your small clusters on the same metal or a couple of metal instances to get that additional savings. But those clusters have to run in the same AWS region. They have to map to the same AWS account, etc. So those are some of the limitations. Yep. And let's see, in the EVM pool, is the VM still migrating,
Let's
Renee, or
check.
is it?
Let's hop over to that really quick. Nope, it is now in a running state. And
Fantastic. So what just happened here is the VM migrated and we kept running ping, and it was, as you can see, it was running, it kept running even after the VM moved to the other host. If we actually trace the ping, we might notice one of the pings where it took slightly longer in terms of milliseconds, and that is likely when the transition happened. For example, I see one instance here where it took about 13.6 milliseconds instead of 9.57, and potentially that may have been the time. But in any case, that's really the interesting and important thing with EMP, where we are really able to rebalance the capacity behind the scenes. If all of the VMs on a metal instance start running high, they start consuming a lot of resources. Well, because we're able to rebalance them, it gives us the flexibility to do a lot more optimization beyond anything that is available on AWS today in terms of cost saving tooling. So EMP is really a brand new compute engine for your EKS clusters, one that operates at a layer below and uses techniques like virtualization and hypervisor, etc., to achieve a level of gains that are just not possible with any of the tooling today. So I think that's the core of our demo today, right, Renee?
yes, that is.
Fantastic. So I think, folks, that's it. Feel free to ask us any more questions if you have now, or if not, you can reach back out to us. You can go to our website and set up time to chat with myself or with Renee. And we have one more question. Any notes regarding stateful sets that we have EBS attached to? That's a great question, and I think that's an important aspect to mention. So EMP is compatible with all workloads, including, most importantly, stateful workloads. And so, for example, for this VM, I don't think we did that, but if you have your workloads with EBS volumes attached, etc., that has no impact on the live migration. The only thing I want to call out is we prefer using the newer generation of EBS volume types, the IO2, IO3, because they support multi-attach. We can still work with GP2, GP3 volume types, but the live migration performance suffers a bit. So that's the only requirement. But otherwise, EMP is in fact designed to work with stateful sets and any other stateful workloads. Yeah, not a problem. Fantastic. So I think that's it, folks. That covers what we had to cover today. And thank you for joining. And Renee, any closing remarks?
Yeah, I mean, first of all, just want to say thank you to the folks who joined. We certainly appreciate the Q&A. And we would love to have a further conversation with you guys if interested. So yeah, we'll be here if we want to revisit this one. Someone would contact me. We are an AWS partner, and we would like to consider offering to our clients. Okay.
That's
So
fantastic. Yeah, our
Carlos,
team will get in touch with you. Yep.
you absolutely will. Thank you.
Great. All right.
So yeah, that is all we have for today.
Thanks, folks. Have a great day.
Thanks, everyone.